A couple of problems that are related to, and let's look at Newton's law of gravitation, because we want to look at a couple of different pieces here. So our universal law of gravitation is that the force is equal to the gravitational constant, mass 1, mass 2, divided by the radius squared. So if I'm thinking I'm dealing with the moon here and I'm dealing with the Earth, so this is the Earth and this is the moon. The r is our distance between these. So this is our r distance. And we are always going to take that this mass is always going to operate as if it's at the center of mass. Same with the Earth. It's always going to operate. So this r is going from one center of mass to another center of mass. That's how we're going to look at this. And this is always dealing with this distance between the two. Now, we said at one point this semester that this is a special case that our special case is that F is equal to ma, or our Newton's second law, because if I have an object at the surface of the Earth, this r becomes fixed, the mass of the Earth is fixed, and this universal gravitational constant is fixed. So our g mass of the Earth divided by the radius of the Earth squared is going to equal our acceleration due to gravity. So that's how we can get this special case of Newton's second law. That's how we get that. All right, so what does this mean for us? Well, first of all, we're now in a circular motion kind of an object lesson here. So we can actually look at a few things that are kind of different. One is I can have the sun here, and I can have Earth, and I can have the moon, and we know that the forces that are being applied are a little different. Now, the way the sun is going to act on the Earth-Moon system is there's probably a center of gravity of the Earth-Moon system, and we can track it there. But if we want to know what the forces are on the Earth because of the moon and the sun, we're going to have to do a couple of things that are a little different. First thing is we're going to have to look at this force, and this is the force that's being applied. And remember, forces are vectors. So if I'm looking at the force that the sun is applying to the Earth, we know that this is how the force is going to go. This is going to be our arrow is going to go this way. The masses attract, so the Earth is going to want to be pulled to the sun. Well, similarly, the Earth is also going to be pulled toward the moon. Okay, because this mass is going to be there. So if I'm looking from the perspective, so this is the perspective of the Earth, it's kind of caught in a tug of war with a really big thing and a small thing. So we've got to take our forces here, and we have to account for the direction. Okay, we've got to account for the direction. So that kind of gives you a background of how we're going to look at this problem. So let's take an object, and we're going to put the object at the origin. So this object is sitting at 0.0, and we're going to have that it's 3 big M, whatever that M is, with 3 masses. We're going to put a really big object over here, And we're going to say that this has a mass of 5m. And this distance, and this is going to be at 0x, and we're going to say 5 meters. And then I've got a teeny tiny object here. We're going to give it a mass m. And this is going to be at, oh, this is, I wrote that wrong. No, I didn't. That's 0x, 5 meters. This is going to be at 3 meters and at 0y. So how am I going to approach the problem? Well, first I'm going to calculate the force between the 3m and the 1m mass. So that's going to be G mass 3m mass 1, and my R is going to be 3 meters squared. And this is going to be a vector. So we could rewrite this as G, and this is going to be 3m times m. So this is 3m squared divided by 9. So I'm going to have a value of G divided by 3m squared. And we know that force is going to look like this. And that's going to be gm squared divided by 3. And it's only in the I direction. And so that's my force vector. So I've got my force vector. Well, now let's do this one. So that's going to be my force between the 5m mass and the 3m mass. So now I've got G, and now I've got my 5m, and I have my 3m. And now that's at 5 squared meters. So now I'm going to have 15g m squared divided by 25. And if I do that, that's going to give me 3/5 g m squared. But we know that that vector is going to look like this because of how we know it's attracted. So this force vector now is going to equal 3/5 g m squared in the j direction. And when I add these two up, the resultant force is going to equal G over 3m squared I plus 3g over 5m squared j. And then we can just use our typical vector notation to be able to work with the problem. So now we can add really strange objects. We know that this resultant force, it's probably going to have us move kind of in that direction because it's going to be more pulled that way than that way. So it's probably going to move kind of that direction as we're looking at how it might be accelerated due to the unbalanced force. And so this is how we're going to start doing a variety of different things. And we'll see this again in electrostatic forces. So for those of you that get to take physics 2, we're going to see this same kind of concept in physics 2 with electrostatic forces. The big issues that we have with gravitational forces like this is that we have distances that are so big that a lot of times these distances, like the Earth-Moon system, is going to act like a point as it goes around the sun, and we're going to continue to have that work there. So that's one of the problems that I wanted to kind of walk you guys through, so you knew how to be able to look at that and looking at balancing of those objects. And from what I saw, based on what people were doing in their homework, those were our two bigger concerns about this week's homework. So, and I will get these posted.